The Mediterranean looks permanent, but 5.97 million years ago, its Atlantic lifeline began to fail. Water exchange narrowed. Evaporation concentrated the remaining sea. Vast salt deposits accumulated, rivers sliced downward, and coastlines moved across areas now buried beneath deep water. For animals, this geological crisis changed the map. Mammals dispersed between North Africa and Iberia during pulses of reduced barriers. Yet the familiar image of creatures marching across one completely dry desert may be too simple. The evidence reveals something stranger. A sea repeatedly transformed, but perhaps never vanished everywhere at once. The trouble began around the Gibraltar Arc, where tectonic movement altered gateways connecting the Atlantic and Mediterranean. Climate affected evaporation and water balance, but shifting land and seafloor controlled how easily Atlantic water could enter. Astronomically tuned rock layers placed the crisis onset near 5.96 to 5.97 million years ago. This was not a plug being pulled in one afternoon. Restriction increased through time. As incoming seawater weakened, evaporation removed water while leaving dissolved minerals behind. The Mediterranean became an enormous concentration basin, primed to manufacture salt on a scale difficult to imagine from its calm modern surface. When seawater evaporates, minerals crystallize in a sequence. Across the restricted Mediterranean, that process created evaporates, mineral deposits including gypsum and halite. Deep-sea drilling later recovered this material beneath the basin floor. In some places, the total evaporate succession approaches or exceeds 1 kilometer in thickness. These are not thin stains around an ancient shoreline. They are a buried salt giant stretching across multiple basins. Its existence proves extreme restriction and repeated concentration. But salt alone cannot tell us whether the deepest Mediterranean became dry land, shallow brine, or a deep body of hypersaline water. Here is the first twist. Scientists do not agree that the entire Mediterranean became one empty basin. The classic reconstruction shows a deep exposed depression dotted with lethal salt lakes. Some sedimentary structures support major emergence and erosion. Yet cores and seismic evidence from certain basins can also fit evaporates deposited beneath deep water. Different parts of the Mediterranean may have behaved differently, and conditions change during the crisis. So, the honest reconstruction is not a single frozen image. It is a shifting patchwork of shrinking water, concentrated brine, exposed margins, and possibly deep hypersaline basins. The strongest evidence for a huge water level fall lies beyond the salt. Rivers respond to the elevation of the water body they enter, known as base level. When Mediterranean base level dropped, rivers cut aggressively into their beds. The ancient Nile carved the Ional Canyon beneath what is now Egypt. Seismic data near Cairo place its deepest channel roughly 1.7 to 1.8 kilometers below modern sea level. That buried gorge is astonishingly deep. It records a river chasing a retreating destination far below its present mouth, then disappearing beneath younger sediment after the crisis ended. The Rhone left another buried incision beneath southeastern France and the modern continental margin. Together, these canyons show that the drawdown was not a minor coastal wobble. Mediterranean drainage systems were reorganized across enormous distances. Waterfalls, steep tributaries, unstable slopes, and rapidly eroding valleys likely developed along exposed margins, although each landscape differed. Estimates of maximum drawdown still vary by basin and method, from several hundred meters to more than 1.5 kilometers. The exact number remains debated. The central conclusion does not. The sea surface fell enough to make rivers excavate extraordinary canyons. Now the crisis becomes an animal story. Lower water did more than expose cliffs and salt flats. It narrowed marine barriers separating Africa from Europe. Mammal fossils record exchange pulses between North Africa and Iberia, including one around 6.2 million years ago. and further movement during roughly 5.9 to 5.3 million years ago. These dates overlap changing Western Mediterranean gateways. The fossils show that animals reached the opposite continent. They do not provide a photograph of the route. The challenge is reconstructing where those travelers crossed and whether their pathway stayed open for generations or only briefly. One likely region involved the changing Bedic and Rift gateway systems around southern Iberia and northern Morocco. As tectonics reshaped channels and water levels fell, islands, coastal plains, or connected corridors could have reduced the journey. Small mammals are especially useful evidence because their fossils can reveal exchanges that dramatic large animal skeletons miss. Still, a faunal exchange does not prove that every strait disappeared simultaneously. Animals may have moved through short-lived windows, using stepping stone landscapes or emergent corridors while other basins remained flooded. The Mediterranean was not simply gone. Its barriers had become unstable and selectively pass. Imagine the crossing at ground level. A small mammal would not perceive a geological crisis. It would follow food, cover, and tolerable ground into newly available habitat. Ahead might lie dry valleys, dusty plains, brackish margins, or narrow channels that changed between generations. Behind it, erosion and salt were remaking the basin. Successful dispersal required more than exposed land. A corridor needed usable water and vegetation along at least part of the route. That ecological filter helps explain why fossil exchanges arrived in pulses rather than as one unrestricted flood of every African and European animal moving both ways. Then the supposedly drying Mediterranean did something unexpected. It received unfamiliar brackish life. During the latest Messinian, deposits called lagomare contain ostracods, dinoflagellates, and other indicators associated with the Paratethys, a vast water system extending east of the Mediterranean. Their presence shows that intermittent connections allowed brackish water and organisms to enter Mediterranean basins shortly before the crisis ended. This breaks the neat desert narrative. At least some areas held water capable of carrying aquatic life, and connectivity could shift direction. The Atlantic was restricted, yet another watery world was briefly leaving biological fingerprints. Scientists still debate the exact lagomare pathways, timing, and number of inflow episodes. Even so, these tiny fossils are powerful witnesses. An ostracod shell only millimeters long can identify a connection invisible in the modern landscape. It tells us that late in the crisis, Mediterranean margins were not merely abandoned salt deserts. They included lakes or brackish environments linked intermittently to eastern waters. For crossing mammals, this means the map remained dynamic. A usable corridor could emerge, fragment, or flood as water sources changed. The same instability that opened routes could close them before a population followed. By 5.33 million years ago, the experiment ended. Atlantic water returned through the Gibraltar Gateway at the start of the Pliocene. Geomorphic evidence and modeling support a rapid Zanclean reflooding, possibly a catastrophic megaflood on geological timescales. Water pouring into the lowered basin would have attacked the gateway, enlarging the channel and increasing the flow. That creates a powerful feedback. More erosion allows more water through, which causes more erosion. Some researchers favor multiple pulses or a less sudden refill, so the exact tempo remains debated. Either way, the Mediterranean became a connected marine basin again remarkably quickly. The reflooding drowned exposed margins, buried river valleys, and separated terrestrial populations that had crossed during lower water. Sediment began filling the Aonal and Rhone canyons, preserving their shapes underground. Marine conditions spread back across basins that had hosted salt, brine, lakes, or exposed terrain. The temporary geography vanished, but its consequences remained in animal distributions. A mammal population does not need a permanent continent-wide bridge. It only needs enough time for individuals to move, breed, and establish themselves before the route closes. Geology can open a door briefly and leave a biological signature lasting millions of years. Today, the evidence forms a forensic chain. Astronomically tuned layers date the onset. Deep drilling reveals the salt giant. Seismic surveys trace buried canyons. Brackish microfossils expose connections with the paratethys. Mammal fossils record movement between Africa and Iberia. Finally, the Gibraltar Gateway and drowned erosion surfaces mark the return of Atlantic water. No single clue reconstructs every phase, and the grandest desert image remain contested. Combined, however, the clues show a Mediterranean transformed by tectonics, evaporation, erosion, migration, and sudden reconnection between 5.97 and 5.33 million years ago. The Messinian salinity crisis was not simply the day the Mediterranean dried up. It was a long sequence of restrictions and reversals. Salt accumulated on an immense scale. Water level fell far enough for rivers to carve kilometer-deep canyons. Brackish organisms arrived from the east. Mammals crossed reduced western barriers. Then Atlantic water reclaimed the basin and erased the roots from the surface. Beneath cities, farms, and modern seafloor, those lost landscapes still survive as salt, sediment, and fossils. If that vanished corridor reopened today, which animal would cross first?